Let us start our class today, an introductory class on diffraction. And we have already done the single slit diffraction in our first class. And today we will start off with the difference between interference and diffraction. Okay, so what is the difference between interference and diffraction? Well, number one, interference is the result of interaction of light coming from two different wavefronts originating from the same source. Interference is interaction of light from two different wavefronts from the same source. Interaction of light from two different waveforms originating from the same source. Okay, but what is diffraction? It is the pattern which results due to interaction of light coming from different parts of the same waveform. So it is, diffraction is the result of interaction of light coming from different parts of the same wavefront. Different parts of same wavefront. Okay, this is very important. Number two, because the difference is very small in both the cases, so if at all you get it, okay, then you have to be very careful when you write it. So interference fringes may be of same width, may not be of same width. When you have Young's double slit experiment or Fresnel biprism, their interference lines are of same, fringes are of same width. But when you do Newton's ring, you have seen that the interference fringes are not of the same width. So fringes may or may not be of same width. Okay, but diffraction fringes are never of the same width. Hey. They are never of the same width. Okay, well, here for interference, the points of minimum intensity are perfectly dark. Points of minimum intensity are perfectly dark. Okay, well, for diffraction, they are not perfectly dark. They are not perfectly dark. Okay, and in interference, all bright bands are of uniform intensity. All bright bands are of uniform intensity. What about diffraction? Are not of uniform intensity. Okay, so this is the basic difference between interference and diffraction. However, we will be doing diffraction only. We have already done single slit. Now you need to know, I have already discussed probably in your class about the difference between Fresnel and Fraunhofer diffraction. Okay, so just you should know, because they ask you what is the difference between Fresnel. There are two types of diffraction, Fresnel diffraction and Fraunhofer diffraction. We'll work on Fraunhofer diffraction, but you need to know the difference. Well, in this type of diffraction, Fresnel diffraction, the source of light or screen or both are at finite distances from the obstacle or aperture. So remember, with Fresnel diffraction, source, light, screen or both are at finite distances. So source or screen or both are at finite distances, okay, from the obstacle or finite distance from what? From the obstacle or aperture. Okay, all right. So no lenses are used over here to make the rays parallel or convergent. The incident wavefront is not plane but is either spherical or cylindrical. This comes as an MCQ. Incident wavefront is not plane. It is either spherical or cylindrical. Okay, all right. So here, therefore, you see the phase of secondary wavelets is not the same at all points in the plane of the aperture or the obstacle where the diffraction is taking place. Okay, and you can divide the wavefront into large number of small elements or zones in Fresnel diffraction. Okay, and one can observe that the effect of any point due to a particular zone will depend on the distance of the point from the zone. Okay, so basically this is the difference. This is the main point which you have to put down when you talk of Fresnel type of diffraction. Okay, but when you talk of Fraunhofer diffraction, then what happens? Well, in this type of diffraction, the source of light and the screen are effectively at infinite distance from the aperture or obstacle, which causes diffraction. Okay, so the source of light or the source of light and the screen are effectively at infinite distance from the aperture or obstacle. Okay, which causes diffraction. All right, now this may be achieved by using two convex lenses, one to make the light from the source parallel before it falls on the aperture and the other to focus the light after the diffraction on the screen. This arrangement in fact removes the source and the screen to infinity. If you use a pair of convex lens, okay, it effectively removes the source and the screen to infinity. Well, the incident wave front is plane. This is important here. Therefore, because you have removed it to infinity, the incident wave front is plane. It's a plane wave front, and the secondary wavelets which originate from the unblocked portions of the wave front are in same phase at every point in the plane of the aperture. So you have a plane wave front, the secondary wavelets are at same phase. These secondary wavelets of the wave front, okay, the secondary wavelets which originate from the unblocked portions of the wave front, you have the secondary wavelets, as you understand, they are at the same phase at every point in the plane of the are at the same phase at every point in the plane of the aperture. Okay, so these are the two basic differences between Fresnel and Fraunhofer diffraction. Now, if you remember, when we had moved to the single slit diffraction phenomena, I will not go into the details of it because I have already done that in your class. Okay, so when we do the single slit diffraction phenomena, then what happens? As you see, well, so for single slit diffraction phenomena, we have observed the resultant R for single slit diffraction. The resultant R that we observed, we had done this vectorially. I am not going to repeat this in class. Well, we have observed that the resultant R is equal to A sine of alpha by alpha, isn't it? That's what we saw for the resultant R. A sine of alpha by alpha. This is the resultant R that we obtained from single slit diffraction phenomena. Okay, what is alpha? Well, alpha was the phase angle, isn't it? So we have seen from our study that alpha is equal to if you remember the diagram of single slit diffraction, we had started with diffraction at different angles like this. Okay, so we had drawn that vectorially to provide the resultant R. So this was R, okay, the vector R. This made an angle theta, and the phase angle, if you remember, we had taken it as D. If you just consult the pages, this was the phase for every single angle that we had considered, isn't it? Now, well, we had taken, if you remember, A was the amplitude. So every portion we had considered, each of them having the same amplitude A. So this was A, this was having amplitude A, and this was having amplitude A, isn't it? So if you remember, we had taken alpha as A sine nd by 2. Okay, all right, if you remember alpha, because after we had calculated the phase difference, we had seen that, well, 2 alpha was equal to A sine of nd. Okay, all right, and alpha was equal to, well, A sine ND by 2, isn't it? We got this as A sine ND. No, wait. We are making a mistake over here. Let's see. I think I have to just go back a little bit for the derivation. We actually had the resultant R over here. This resultant R, from our previous derivation, we had it as equal to A sine of ND by 2 divided by sine of D by 2. Okay, alright. Now, what we did over here was that, well, we had considered n to be infinitely large and the amplitude A and phase difference D are infinitely small. So the product NA and ND are finite. Okay, NA is equal to NA, here we have ND by 2 and here we have D by 2, isn't it? So NA, if we take, well, that is taken as A, okay, and well, ND is taken as 2 alpha. Okay, how are you getting NA? If you take ND over here by 2 as alpha, then ND is equal to 2 alpha. Okay, now D will be equal to 2 alpha by N. Now this, if you substitute for R, what do you get? This, if you substitute for R you get as, just because I'm doing it, okay, what do you get for R? R is equal to, let's put it, okay, sine of ND by 2, so sine of A sine of alpha, and what is D by 2? Alpha by N. Okay, sine of alpha by N. Now because N is large, isn't it? So sine of alpha by N goes to alpha by N. So what you have over here, what you had over here is NA sine of alpha by alpha. Okay, and this NA you put as equal to A. Put NA as equal to capital A. So what you get for R is A sine alpha by alpha. Okay, this is a very important derivation that we had obtained for single slit. For the resultant R, okay, the intensity is the square of R. I is equal to R square. So I is equal to A square sine square alpha by alpha square. I'm sorry I had taken so long for this video, but basically today I want to start my class with double slit. Okay, so this is introduction. This was what we had already done in the previous class. It had taken too long a time as a video. Okay.